High School AP Chemistry. This is the lecture video on Unit 5, Intermolecular Forces.
All right, so let's do a quick review. In this course, we've talked about three types of chemical bonds, one of those being metallic bonds. Now, we don't deal very much with metallic bonds because there's not really a lot to talk about. They are bonds between metal atoms, and they basically occur when metal atoms, they can all be the same atom, copper atoms in this example, are together. Generally, metal atoms have a very large number of orbitals, 3, 4, 5, and 6 orbitals, which means that their valence electrons are shielded heavily from their own nucleus. Because of that, the valence electrons are not held very tightly to any one atom. And so metallic bonds occur when the valence electrons just kind of jump around freely between atoms. It's called an electron sea model. And you can have just a whole lot of these copper atoms together, and the electrons are just kind of wildly running around like that. So that's a metallic bond. The other type of bond, next type of bond that we have talked about extensively, are ionic bonds. And a simple example that we've seen many times is sodium and chlorine. Sodium has a valence electron that it easily loses because it has low electronegativity. Chlorine, being a non-metal, has high Sodium has low ionization energy, so it easily gives up an electron. It does not take much energy to take the electron away from sodium. Chlorine has high electronegativity, so it likes to pull in outside electrons. Technically, that is electron affinity, but we just kind of loosely refer to it as electronegativity. And so what happens is the electron jumps from the sodium to the chlorine. Chlorine becomes a negative anion, the sodium becomes a positive cation, and that causes them to bond together. And they don't simply bond as one sodium and one chlorine, they bond in these big structures called lattice, crystal lattice structures, as you see right there in the image. It's kind of like apartments in an apartment building or bricks in a wall, and they tie together with a lot of other sodium and chlorine atoms. Next, we have covalent bonds. Covalent bonds are between nonmetals, and they share electrons. So here we see an oxygen atom and two hydrogen atoms. Both want to complete their octet. So what they will do is they will move in. Hydrogen now has 2 electrons, one of them that it brought itself and one of them that's being shared by the oxygen. And that gives it 2 electrons. That's a complete octet for hydrogen. The oxygen, meanwhile, as you can see, has 8 electrons surrounding it, and that's an octet for oxygen. So that's a covalent bond, and that is between nonmetal to nonmetal, and that's when electrons are shared. The focus of this discussion on intermolecular forces deals with covalent bonds. Covalent bonds form independent structures called molecules. So if we take these three, we're going to ignore the other two for now. They don't apply to this discussion, and we're going to simply talk about the covalent bonds. So only covalent bonds form separate structures called molecules. So sodium and chloride is not an independent structure. It's part of a brick wall, as we just mentioned. But water is an independent molecule. It's an independent structure. 2 different water molecules can separate and go in different directions. So what intermolecular forces, which we call IMF, so get used to that abbreviation, what they determine is whether the molecules will stick together or not. It's just that simple. Are they going to stick together, or are they going to separate and go off in their own separate ways? The key point, though, here is that intermolecular forces are much weaker than covalent, ionic, or metallic bonds. Okay, so phases of matter, something most of you are familiar with. There are 3 phases of matter that we deal with: solids, liquids, and gases. So a solid retains its own shape. It's incompressible, meaning you can't squeeze it down any smaller than it is. And it does not flow. So those ice cubes, assuming they don't melt, they just sit there and they maintain their shape and the amount of space that they take up, the volume. Liquids take the shape of the container they're in, so that water in that glass could either be in that glass, or you could pour it into a tall, narrow glass or a short, wide glass. It'll be the same amount of water, it's the same volume, but it takes on the shape of the container. It's incompressible. Just like solids, liquids are very incompressible. Their molecules are side by side, they're right next to each other, and so you can't squeeze them down really much farther than they already are. They also diffuse slowly in other liquids. So if you put a drop of food coloring in water, it'll slowly spread out throughout the water. But finally, gases. Gases take the size and shape of their container. So if you have a bottle of perfume, all of the perfume molecules are inside that little bottle. If you take the top off, particularly on a warm day, those molecules will spread out and spread out to the volume of the entire room. So they not only don't have a constant volume, they can either be in a little bottle or spread out among the entire room, but they take on the shape of the container that they're in, either the bottle or the room. They do flow and they diffuse rapidly in other gases. Okay, so what really the whole thrust of this subject is that intermolecular forces versus kinetic energy. So intermolecular forces are a battle between kinetic energy and Coulombic attractions. So on the one side, you have kinetic energy, which is caused by higher temperatures. So higher temperatures put more energy into a molecule. That causes them to break apart from other molecules. And once they've broken apart, if they actually become a gas, it will determine how fast they can move around. Also, pressure has an effect on this whole process. Pressure doesn't add kinetic energy to a molecule, but if you have lower pressure, that is less pressure from the atmosphere pushing in on the molecule, it doesn't take as much energy to break the molecule away from other molecules. So pressure, how much a molecule wants to break away from others, is a function of the temperature, how much energy you put into it, and how much pressure or how little pressure you put on it that allows it to break away and become separate and separate from other molecules. The other force is Coulombic attractions, and those are the electrostatic forces of protons and electrons that attract molecules to each other. Coulombic attractions don't change. Water molecule has a certain amount of Coulombic attraction. What does change is the kinetic energy, how much energy you put into that molecule to allow it to either break away from another water molecule, or how little energy you put into it that'll allow it, that'll cause it to just stick to another water molecule. Okay, so now intermolecular forces and temperature pressure. Generally, matter moves from gas to liquid to solid in two ways. So now we're going from the higher energy gases down to intermediate energy liquids, down to lower energy solids. When molecules form a solid, that means they're stuck together really tightly, which means they don't have as much energy. So two ways to do that. One is reducing the temperature so that molecules decrease energy and move closer together. So this just gives you a simple illustration. 20 degrees is roughly room temperature. If you drop the temperature in the room down to 0 degrees, then these two molecules that were floating around as a gas will come together and either be a liquid or a solid. So they'll lose energy, and because they have an attraction to each other, and we'll talk about that attraction in just a moment, they will come together. The other way you can get molecules to go from liquid to solid to gas is by pushing them together, just by brute force, by increasing the pressure while keeping the temperature constant and squeezing the molecules closer together. So if we imagine the molecules in this container are a gas, they're floating around, you can simply push them down like that and literally just squeeze them together by brute force to get them to come together into either a liquid or a solid. Okay, so intermolecular forces. If the kinetic energy overwhelms the Coulombic attractions, in other words, kinetic energy is much greater than the Coulombic attractions, then the molecules separate and exist as a gas or a vapor. So this simple little illustration shows that the molecules are moving around freely. They're not attracted to each other, and they just fly about rather randomly, occasionally bump into each other, but that's no big deal. They don't stick together. That's the point of a gas or vapor, because they have enough kinetic energy, which gives them enough kinetic energy, which causes them to just stay separate from each other. Okay, so if the kinetic energy and the Coulombic attractions are about equal, then the molecules will stick together, but they can still move around each other. And these are molecules that would form liquids. So if we look at this illustration, we see that the molecules are moving around kind of randomly, just like as the gas molecules were. But unlike the gas molecules, they don't separate from each other. They have enough intermolecular force between them, and the kinetic energy in them is low enough that they don't totally break apart from each other the way gas molecules did. So this is the way that liquid molecules would move around, and that's why water in a cup just sloshes around. You can swirl it around and slosh it around, and it moves around pretty freely, but doesn't come apart. Now, if the kinetic energy is low compared to the intermolecular force, then the molecules will stick together in fixed places, and this produces a solid. So this example here is hydrogen sulfide, which becomes a solid at a pretty low temperature, minus 82 degrees centigrade. But the point is simply, you see the molecules are moving. Just because something is a solid, like a piece of metal, doesn't mean the atoms and molecules in it are not moving. They are definitely moving. There is nothing in the universe that is standing still. But while these molecules are wiggling around, you'll notice that they can't change positions. They can't break away from each other like a gas. They can't even change positions like a liquid. So yes, they're wiggling. If you put more heat into them, higher temperature, they'll wiggle even harder. Eventually they would break apart. But as they are right now, they're just staying in place. They can't move around, and they are wiggling about. Okay, this table is really a summary of everything we're talking about in this unit. It's the interacting molecules or ions. So the first question you ask is, are ions involved? Remember, an ion is a positively or negatively charged atom. Like sodium is a positive ion called a cation. Chlorine is a negative ion called an anion. So are there ions involved, positive cations or negative anions? So now we're going to start off going to the right. If the answer is yes, then the second question you ask is, are polar molecules and ions both present? Again, when you think polar molecule, just think of a water molecule. A water molecule is electrically neutral, meaning in the total water molecule, there's just as many protons as there are electrons. It has a balanced charge. However, because oxygen is far more electronegative than hydrogen, the electrons are pulled over to the oxygen side of the molecule. It's not a symmetrical molecule. So the oxygen side of a water molecule has more electrons, and therefore it's negatively charged, and we say that it has a negative dipole. The hydrogen side is more positively charged because the electrons are pulled away from it, and all that's left on the hydrogen side are those two protons, which are positively charged. So that's a polar molecule. So if polar molecules and ions are both present, then you have an ion-dipole force. Polar molecules, dipoles, they mean the same thing. So examples would be if you put potassium bromide into water, the potassium bromide would dissolve. You remember from your solubility rules, if you can remember back that far, potassium breaks apart with anything that it's with. So the potassium would become a positive cation, the bromine would become a negative anion, and those would be attracted to the different ends of the water molecule. We'll talk about that a little bit more in a moment. Okay, now what if the answer to that question are polar molecules and ions both present? We know that ions are present for this part of the graphic here. But if there's no polar molecules, then you simply have ions, and that would be ionic bonding. Sodium chloride, table salt, or ammonium nitrate. Remember, ammonium, NH4, is a positively charged cation, and nitrate and NO3 is a negatively charged anion. So they would bond together to form an ionic bond. So we've talked a lot about ionic bonds in this class. Now let's go back to the top center, and let's go to the other direction. So are ions involved? Let's say no. Then the next question is, are polar molecules involved? Let's say that they are. Then there's two questions to ask. Are hydrogen atoms bonded to nitrogen, oxygen, and fluorine? We're going to talk about hydrogen bonds in just a little while. But if the answer to that is that there's a hydrogen bond atom bonded specifically to nitrogen, oxygen, or fluorine, it can't be any other element, If the answer to that is yes, then you have hydrogen bonding. So examples of that would be H2O, where hydrogen is bonded to oxygen, NH3 ammonia, where hydrogen is bonded to nitrogen, or HF, hydrofluoric acid, where hydrogen is bonded to fluorine. In those three cases, you have a hydrogen bond. What if the answer to that is no? We do have polar molecules, but you don't have a hydrogen atom bonded to nitrogen, oxygen, or fluorine. If the answer to that is no, then you have dipole-dipole forces. That would simply be a molecule that has a positively charged end and a negatively charged end. And the positively charged end of one of those molecules will want to be attracted to the negatively charged end of a similar molecule. So hydrogen sulfide would be one, and there are many, many examples of that. The next one finally is, are polar molecules involved? If we go way over to the left and we answer that question as no, then we have no polar molecules. That means we only have non-polar molecules. And something called London dispersion forces are the only types of forces involved. So methane is a non-polar molecule, and it attracts other methanes only by London dispersion forces. Same with iodine. So this table, I'm starting off showing you this table, but you want to go back and refer to this table after you know what all these types of forces and bonds are later on after the lesson. Okay, let's keep going. So ion-dipole forces, we'll start with those. So on the left, you see a salt crystal, and it has those negative charges are the chlorines, those are the negative ions, the anions, and the positive charges are the sodiums, the NAs, those are the positive ions, cations. And so as it sits on, when it's dry, when it's not in liquid, it forms this crystal lattice structure like bricks in a wall. So table salt consists of Na plus and Cl minus ions arranged in a lattice structure like bricks in a wall. Now, a water molecule is a polar molecule with a negative dipole pointing towards the oxygen atom, and a negative and the negative oxygen side of several water molecules point towards the Na plus sodium ion. So in other words, the oxygen side of a water molecule, of a whole bunch of water molecules which are negatively charged, they kind of gang up on one of the sodium ions and they pull it away from that salt crystal. So you'll notice where that arrow is pointing, you have 4 water molecules surrounding that one plus sign, that sodium ion, and the negative end of each of those water molecules is pointing in the direction of the plus sign. So what that would do is those 4 molecules would have enough force to pull that plus sodium ion away from that crystal lattice structure over on the left. Now the positive hydrogen side of several water molecules, that would be the hydrogen side of several water molecules, points towards the chlorine, the negative ion. And these are called, both of these together, both of these types of attractions are called ion-dipole forces because they involve the dipole of a polar molecule, water in this case, with the ions, either sodium or chlorine. Depending on whether it's the positively charged sodium or the negatively charged chlorine will depend on which side of the water molecule is attracted to it. And you'll notice about 4 water molecules gang up on that chlorine and pull it away from the salt crystal. So both of these effects are called ion-dipole forces. All right, now dipole-dipole forces. Dipole-dipole forces attract polar covalent molecules to each other. Hydrochloric acid, HCl, is polar because a highly polar chloride atom, it should actually be a chlorine atom. It's not ionized, that would be chloride. So a highly polarized chlorine atom pulls the hydrogen electron towards it. So that means the chlorine is going to be a negative dipole, and the hydrogen, which is having its electron pulled away from it, but not totally away from it, just kind of towards the chlorine, that becomes a positive dipole. That's the sigma minus for the chlorine and the sigma plus, delta minus for the chlorine and the delta plus for the hydrogen. So below, the positive hydrogen side of the HCl molecule is attracted to the negative chlorine side of another HCl molecule. So in other words, that hydrogen is having its one electron pulled over towards the chlorine on the far left. what that does is that leaves that hydrogen proton, which is the nucleus of the hydrogen, exposed. And so it then is attracted to the other chlorine. And that is what's called a dipole-dipole, where a positive dipole of one molecule is attracted to the negative dipole of a second molecule. London dispersion forces. London dispersion forces are temporary changes in polarity of a molecule due to the random movement of electrons. In other words, if the electron in atom 1 is over on the right-hand side of atom number 1, then it will push the electron in atom number 2 also over to the right. Why? Because they repel each other. So the electron in atom number 1 will push the electron in atom number 2 to the right. Now you might ask, why doesn't it happen the other way around? It could, but we're just in this example saying that atom number 1 is going to push the electron in atom number 2 to the right, and the electron in atom number 2 is going to push the electron in atom number 3 to the right. So you'll notice you have these temporary dipoles, because remember, those electrons aren't going to just sit there. They're going to go around and around and around like this, and they're going to continue to circle their nucleus. But what will happen is that these electrons will not only push another atom's electron away, but now what you have is a situation where the electron in atom 1 pushes electron in atom 2 to the right. Now what you have is a negative dipole, temporary negative dipole, because remember, these electrons are constantly buzzing around all over the place. So you have a negative dipole on the electron in atom 1, and it's being attracted somewhat to the nucleus, the proton, in atom number 2. Similarly, the electron in atom number 2 is pushing the electron in atom number 3 over to the right, and while it does that, the electron in atom number 2 has an attraction to the nucleus of atom number 3. It's not very strong. It can't totally jump over there, because if that happened in this case of a hydrogen atom, you'd have a hydrogen atom with 2 electrons, and that's impossible. That's physically impossible to happen. But it can have a weak attraction. London dispersion forces of the types of forces that we've just talked about are the weakest of them all. So when the electron in the hydrogen atom on the left moves to the right side, it pushes the second atom's electron to the right. If this effect repeats throughout many atoms, it creates a temporary polarity that attracts atoms to each other. So it's a very weak attraction, but it is there. Where this particular type of attraction becomes really important is in nonpolar molecules. Nonpolar molecules are attracted to each other. You might ask, how can that happen if they don't have a pole, if they don't have a positive or negative end to them, the way polar molecules do? Well, this is the answer, that these London dispersion forces can create these temporary poles, positive and negative sides to the nonpolar molecules, and that will allow them to be attracted to other nonpolar molecules. Okay, so dispersion forces, London dispersion forces, LDF, are small but can produce a stronger attraction between large molecules with many electrons. So let's take some examples. Here's a gas, it's methane, CH4, one that we have a lot of experience dealing with. So a CH4 molecule has weak London dispersion forces because it has only 10 electrons. If you count up C and 4 H's, is going to give you 10 electrons in all. CH4, by the way, is called methane, and it has a very weak London dispersion forces and is not attracted to other methane molecules. Therefore, methane at normal room temperature and pressure is a gas. It floats around. Now, let's take octane, which is C8H18. It has 66 electrons, a lot more electrons. This is strong enough to make octane a liquid with other octane molecules. Why? Because those London dispersion forces, which between just a single electron and a single proton are very weak, when you get enough electrons all pushing each other to one side, they can make the polarity of an octane molecule fairly strong. And so it's going to stick to other octane molecules. The negative side of one octane molecule will stick to the positive side of another octane molecule. And octane basically is gasoline. It's what people put in their car, and we all know that that's a liquid. So that would be true. So octane would be a liquid at normal room temperature. Finally, an example of a solid, which is a hydrocarbon, a CH molecule. Again, this is a nonpolar molecule. All three of these are nonpolar. Is paraffin, which is candle wax. And you can see it has a fairly large number of carbons and hydrogens. That's about 322 electrons in all. This many electrons form strong enough attractions to make paraffin a solid at room temperature. So candle wax is solid at room temperature. And that's because when you have 322 electrons being pushed over to one side of a paraffin molecule, and it's going to push 322 electrons in another paraffin molecule over to the other side of that molecule, and then those 322 are going to be attracted to the protons in the other molecule. There is a strong enough temporary dipole to allow paraffin molecules to stick together fairly strongly like a solid. And there are some solids and hydrocarbons that are nonpolar that are even stronger than candle wax, that are even stronger than paraffin. So shape also affects the strength of London dispersion forces. Longer, flatter hydrocarbons, that is molecules with just hydrogen and carbon, such as N-pentane on the left, form stronger London dispersion forces than round neopentane molecules because they fit together tighter and with less space. And you can kind of just logically see that. The molecules on the right can kind of lie on top of each other and their atoms get closer together. So that means their electrons get closer together. So they can form stronger London dispersion forces. Those roundish kind of molecules on the right, they can't really get very close to each other. Just one point at each molecule can get close to another point in another. To the three most electronegative second row elements, nitrogen, oxygen, and fluorine. So when oxygen pulls the electrons of a hydrogen atom that's bonded to it towards it, an exposed hydrogen nucleus, basically a proton, is left kind of sticking out there exposed because its electron is being pulled towards the oxygen. This proton is attracted to the lone pair of another molecule with a nitrogen, oxygen, or fluorine atom. The hydrogen atom has a fairly strong attraction to the other atoms, though it is not nearly as strong as its own covalent bond. So the other atom can't pull that plus sign, that proton, away from its original atom, but it does have a fairly strong attraction. So you see how each of these protons, which are really the hydrogen atom, are attracted to the lone pair of another water molecule. And that's called a hydrogen bond. Again, it has to be between a hydrogen atom and either a nitrogen, oxygen, or fluorine atom, the lone pair that are in a nitrogen, oxygen, or fluorine atom. So, for a hydrogen bond to occur, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine, and must be attracted to the lone pair of another nitrogen, oxygen, or fluorine atom. For example, a hydrogen atom that's attached to a carbon atom cannot hydrogen bond. The hydrogen has to be directly attached to a nitrogen, oxygen, or fluorine. So let's look at the first two molecules on the left. You can see that these are two water molecules, and that the proton, or the hydrogen atom of the higher of the two, is attracted down to that lone pair, the one on the lower left, and that would form a hydrogen bond. Now, here a hydrogen atom on the water molecule bonds with a lone pair on a nitrogen atom. So in other words, you can mix and match. It can be a molecule with an oxygen atom, the hydrogen atom attached to an oxygen atom bonding with the lone pair on a nitrogen or even a fluorine atom. So you'll see that in the middle there, where that middle set of arrows is, that plus sign, that hydrogen atom is being pulled and attracted to the lone pair on the nitrogen. So right there. And finally, you see on the right side, you see a hydrogen atom on the nitrogen bonds with the lone pair on a fluorine atom. So you can have any of those combinations, nitrogen, oxygen, fluorine, bonded with each other, as long as the hydrogen is attached to one of those three atoms, not to any other type of atom, and it's being attracted to the lone pair on one of those three atoms. And that's called a hydrogen bond. And of all of the types of intermolecular forces we're talking about, these really should be called hydrogen forces because they're not chemical bonds the way a covalent or an ionic bond is. But these are the strongest. Hydrogen bonds are the strongest, and yet they're still much, much weaker than a covalent bond or than an ionic bond. So hydrogen bonding works because nitrogen, oxygen, and fluorine pull the electrons away from the hydrogen so completely that an exposed proton is left sticking out from the molecule, and that allows it to then be attracted to the lone pair of another molecule. So hydrogen bonds of water are stronger than the hydrogen bonds of say, ammonia, NH3, or hydrofluoric acid, HF. Why would that be? Well, as you can see, when water has two lone pairs and two hydrogen atoms. So that's a 1-to-1 correspondence. So if you have a lot of water molecules, then that means every hydrogen atom on a water molecule somewhere in that water is going to find an unattached lone pair. So it's a 1-to-1 correspondence because you have two hydrogens and two lone pairs on each water molecule. So there's one hydrogen on a water molecule for each lone pair on the other water molecule, and that's a perfect match. Now let's compare that to ammonia, where nitrogen is bonded to hydrogen. Ammonia has only one lone pair, as you can see, on each molecule, and there's three hydrogens. So there's a 3-to-1 ratio of protons on an ammonium molecule for every one lone pair. So it's like if you go to a dance and there's 3 times as many guys as there are girls, then a lot of the guys aren't going to have a dance partner because there's not an even balanced ratio. So there's no lone pair to bond with those two particular hydrogen atoms. Fluorine is just the opposite. So in hydrofluoric acid, it has only one hydrogen proton for every 3 lone pair. So in that case, if you have 3 times as many girls as you have guys, then the opposite situation arises, but not everybody's going to have a dance partner. So that's why water it actually forms stronger hydrogen bonds because there's a perfect 1-to-1 relationship between protons and lone pairs, whereas that's not true for ammonia, for hydrofluoric acid, or for anything that's has a nitrogen as a central atom or a fluorine as a central atom. And there's the no hydrogens for those two lone pair. So water, hydrogen bonds. So with water, hydrogen bonds most effectively and has the strongest hydrogen bonds. So let's compare the intermolecular forces here. Generally, the following is the order of strength of different intermolecular forces from weakest to strongest. London dispersion forces are generally considered the weakest because they consist of temporary dipoles. All molecules have London dispersion forces, even polar molecules, even hydrogen bonding molecules, but they're so weak that they don't play an important role in the bonding of those molecules. And keep in mind that there are some solids that are pretty strong that are nonpolar that only have London dispersion forces. So if their molecules are big enough and have enough electrons, London dispersion forces can be fairly strong, but they're still considered to be the weakest of the intermolecular forces. Dipole-dipole forces are next because they consist of the positive negative ends of electrically neutral molecules. Again, just think of two hydrofluoric acids attaching to each other. One has a positive end on the fluorine side and a negative end on the fluorine side where the electrons are pulled toward, and a positive end on the hydrogen side where basically you have an exposed proton sticking out there from the hydrogen. Next is ion-dipole forces. They're stronger because they contain a fully charged ion, such as a sodium Na+ or a chlorine Cl-. So that's a fully charged ion. It's not just a slightly charged end of a polar molecule. and then they attach with the end of a molecule of the opposite charge, such as we talked about sodium chloride in water. Finally, hydrogen bonds are considered the strongest. Hydrogen bonds formed by water molecules are the stronger than the other hydrogen. Okay, now we're going to talk about melting points and boiling points of some molecules that appear to be fairly similar in structure, and yet some of them have very substantially different melting points. So again, what causes a melting point or a boiling point to be greater? It's that the intermolecular forces between the molecules are stronger, so it takes more energy, more heat to get them to break apart and, for example, boil. That's what boiling is when one molecule flies off into the atmosphere and then another one does the same thing. So if they have very strong intermolecular forces between them, it's going to be harder for them to do that. It's going to take more energy, or a higher temperature or a higher boiling point to get them to do that. So let's look at these lines here. It looks a little confusing, but just follow these line by line. So let's look at the light blue line on the top. So you'll see that the boiling point for water is a lot higher than for some similarly structured molecules. H2O versus H2S, H2SE, and H2TE. So all of them have two hydrogens bonded to an atom that is in the same period as oxygen. So why is oxygen's boiling point so much higher? In other words, why does oxygen have so much stronger intermolecular forces than the other three? So let's go ahead and read this. Hydrogen bonds are the strongest intermolecular forces. Only nitrogen, oxygen, and fluorine can hydrogen bond. So H2O has a much higher boiling point than H2S, H2SE, or H2TE, the light blue line, because it has the strongest hydrogen bonds. In fact, the other three don't even have hydrogen bonds. They just simply have dipole-dipole bonds. So that explains why oxygen's boiling point is so high, because its molecules stick together stronger than the other three, because it has hydrogen bonds and the other three don't. Let's go down to the red line. And there you see HF, hydrofluoric acid, and it has a much higher boiling point than HCl, hydrochloric acid, HBr, hydrobromic acid, or HI, hydroiodic acid. Why is that? And it's really the same reason. HF has a higher boiling point than HCl, HBr, HI, because fluorine can form hydrogen bonds where the other molecules can only form weaker dipole-dipole bonds. So again, the hydrogen bonds being stronger, and hydrogen can only form that with fluorine, not with any of the others, and therefore it has a higher boiling point. Okay, so again, reading the top, stronger intermolecular forces cause substances to melt and boil at higher temperatures because the molecules stick together better and don't separate easily. So let's move on down to the green line. And we see that ammonia has a slightly elevated boiling point, not as dramatically as the other lines above. In fact, you can see SBH3 has a boiling point that's just about the same as ammonia NH3. So, but again, the reason that ammonia's is a little bit above pH3 or ASH3 is that NH3 has a higher boiling point than pH3, ASH3, or SBH3 because NH3 hydrogen bonds while the others don't. But you remember that ammonia doesn't have a very good hydrogen bond because it has 3 protons, 3 hydrogens for every one lone pair. So it's not a good match the way water is. And therefore, while it does hydrogen bond, the hydrogen bond is not of the same good quality as it is for water. Now, finally, let's look at the bottom line, the darker blue line. That's a little bit different. These are non-polar molecules. Methane you recognize down there on the lower left. It's non-polar. So are the rest of them. Okay, so why does methane have a lower boiling point than SiH4, GeH4, or SnH4? And the answer is the bottom line from CH4 to SnH4 contain nonpolar molecules that have only London dispersion forces. London dispersion forces are stronger with larger molecules because they have more electrons. So SnH4 has more electrons than CH4 and the others as well. And so therefore, because it's a bigger molecule, it has stronger London dispersion forces. That's the only kind of forces that nonpolar molecules have, and that's why the order of boiling point goes in that direction. Okay, phase diagrams. Phase diagrams is something you might have come across in 8th grade science. It's simply a diagram that has pressure on the vertical axis and temperature on the horizontal axis. And a phase diagram is done for a specific substance. So you can have one for water, a completely different phase diagram for carbon dioxide, a different phase diagram for hydrogen gas, and so on. Every element or compound has its own phase diagram. And it simply tells at what combination of pressure and temperature a substance is going to be a solid, a liquid, or a gas. So at higher pressure, substances tend to become solids because the molecules are squeezed together, and so they want to tend towards solids. At lower temperatures, substances tend to become solids because they lose their kinetic energy, and therefore they kind of fall together and stick together from the intermolecular forces. So this is just a generic phase diagram for no particular compound. Let's take a look at it. You should know all of these different arrows that are on it and what are these different phase changes called. So let's start in the upper left between solid and liquid. These are two terms you've known all of your life. Melting, when you go from solid ice, solid water, which is ice, down to liquid water, that's called melting. And when you go in the other direction, liquid water to solid water, ice, that's freezing. So you already know those terms. If we move over to the left, if water goes from a liquid to a gas, that is steam, for example, or just evaporates, that's called vaporization. When it goes in the other direction from vapor down to a liquid, that's called condensation. That's why you see water on leaves early in the morning, because vapor in the air is condensed down to a liquid. And then the two that you may not be familiar with are going from a solid to a gas, because that's a fairly unusual circumstance. So sublimation is going from solid directly to gas. It doesn't go through the liquid phase. Normally things go from solid to liquid to gas, but in the case of sublimation, if you have things at a low enough pressure, then the solid molecules will just immediately break off and go immediately into the atmosphere without going into the liquid phase. That's called sublimation. That's what dry ice does, which is frozen carbon dioxide. When you see all that smoke coming off of dry ice, that's what's going on there. And going in the other direction is a term probably nobody knows. It's called deposition, and that's going from a gas back directly to the solid phase. Okay, so the three states of matter are solid, liquid, gas. A phase diagram shows the state of a substance at a combination of temperature and pressure. The names given to phase changes are shown in the phase diagram. All right, so for all substances, if we hold the temperature at T2, so I've put a couple of points on here, you'll see A, B, C, and D. So let's start over on the right. If we hold the temperature T2, so that means we're staying at a constant temperature, and increase the pressure from C to D. So as you go up on the vertical axis, you're going to higher pressure. Then the substance will condense from a gas down to a liquid. In other words, you're literally just by brute force squeezing the gas molecules or the vapor molecules together so that they are forced to stick together and become a liquid. For most substances, if we hold the temperature at T1, so now we're moving over to where it says T1, and up above it you have point A and point B. But for most substances, if we hold the temperature T1 the same, so you don't change the temperature, but you increase the pressure from A to B, then the substance will freeze from a liquid to a solid. And again, by just purely brute force, you're squeezing the molecules that are liquid tighter together so they stick in place, they can't move around, and they become a solid. So higher pressure squeezes molecules into a tighter position and creates a solid. All right, now water is very unusual. Water has a backward sloping curve between the solid and the liquid, and that's what the arrow is pointing to. So you'll see where point A is and point B is. So point A is at a lower pressure, and that's ice, solid water. If you go to a higher pressure, then the water actually liquefies. It becomes liquid water. That's where point B is. That's just the opposite of just about every other substance on Earth. Usually when you squeeze the molecules tighter together, they go from liquid to solid. Water is the other way around. If you squeeze the molecules tighter together, they go from being a solid to being a liquid. Why is that? It's very unusual, and this could be something they ask you on the AP exam. So let's read over here on the right. If the temperature is held at T1 and the pressure is increased from A to B, then water will go from solid to liquid. This is different from most other substances. High pressure pushes water molecules closer together. Liquid water molecules are closer together, so high pressure creates liquid water. Low pressure allows the water molecules to spread out and create hydrogen bonds, so low pressure creates solid water. The next slide will show you why that is. Or actually a couple slides. So let's finish up with the phase diagram here, and let's define some more terms. The critical point of a phase diagram is the pressure and temperature at which gas and liquid phases cannot be distinguished. In other words, when the pressure is so high and the temperature is so high, you get to a point where you can't tell the gas from the liquid, the vapor, the water vapor, for example, from liquid water. It's just kind of an in-between state. And that would be point D that was written in by hand up there. That's the critical point. So that's where gas and liquid are really the same. Critical temperature is the highest temperature at which a liquid can exist. If you go beyond the critical temperature, it doesn't matter how much pressure you put on the water molecules or liquid molecules to squeeze them together, they're going to become a gas. They're going to split apart at a high enough temperature. And that's called the critical temperature. The triple point is actually a more common term that you'll come across in phase diagrams. A triple point at point A there is the pressure and temperature at which the substance actually exists as a solid, liquid, and gas all at the same time. So at that point, if you just slightly increase or decrease the pressure or temperature, it'll suddenly switch from being a liquid to a gas to a solid, back to a liquid to a gas to a solid, so on. And that triple point is where it's effectively at all three states at that particular temperature and that particular pressure. Okay, so molecules with high intermolecular forces, what are they? They're molecules that are highly polar, or they're very large nonpolar molecules that have large London dispersion forces. These stick together better, so they have higher critical temperatures than smaller nonpolar molecules. So in other words, you can raise something with strong intermolecular forces to a higher temperature and keep it as a liquid before it breaks apart into a gas. So highly polar and large molecules have higher boiling points than weakly polar and small nonpolar molecules. So just remember those relationships. All right, so compare the phase diagrams for H2O and CO2. Carbon dioxide is on the left and water is on the right. At normal room temperature, which is about 300 Kelvin and 1 pressure atmosphere, that's just what you would feel in the classroom. Theirs are shown on each of these phase diagrams by the letter X. So you can see the heavy red line with the 1, that means 1 atmosphere of pressure. And you can see the X is right about at 300 Kelvin on both of the graphs roughly. So that's normal room temperature. So water is liquid and carbon dioxide is a gas where you see the X's. On the left-hand phase diagram, the X is way over in the gas area. And that's because carbon dioxide at room temperature is a gas. We know that because we breathe it out every time we exhale. And the water on the right-hand phase diagram, you can see is in the liquid range. It's in between the two dark lines and it's in the liquid range. So at room temperature, water is a liquid. Okay, now we're finally getting to the point of why is solid water, ice, less dense than liquid water, And this is different than almost any other substance on Earth. So solid water ice molecules are held farther apart by hydrogen bonds, and that's what you see over on the left-hand side. They basically push each other kind of away at a very specific angle. In fact, they form crystal structures. Ice is actually crystal structure. Liquid water molecules are freer to move around and stay closer to one another. This means ice is less dense than water. And that's a very important characteristic because it means ice will float on water. You know that anytime you put ice cubes into a soft drink, the ice cubes float. That's an incredibly, if there wouldn't be life on Earth if that wasn't true. Because if every time a lake froze over and the ice was more dense than water and sank to the bottom, if ice cubes sank to the bottom of your drink and ice sank to the bottom of the lake, it would kill all the life on the bottom of the lake, all the plant life. And eventually it would keep freezing and keep falling, and the entire lake would become a solid block of ice, and all the fish life would die as well. So the fact that this water has this unusual property that solid water is more spread out, that's really what less dense means. The 4 molecules on the left, as you can see, take up more space. They're more spread out than the 4 molecules of liquid water on the right. So that means it's less dense. So that means ice floats on top of liquid water. So here's actually the crystalline structure of ice. So solid water molecules form a hexagonal structure where there is a lot of space between molecules. This makes ice less dense than water, and therefore it floats on top of water. And here's yet another image of that. So stronger intermolecular forces cause substances to melt and boil. It should be at higher temperatures because the molecules stick together better and don't separate. Okay, but anyway, that maybe is a different point, but this is another image of the water molecules in liquid form in particular and in solid form on the right, and you can see they form hexagons, 6-sided figures. Now we're going to get into the concept of vapor pressure. So vapor pressure exists when liquid molecules gain enough kinetic energy to break free and exist in the atmosphere above the liquid, creating the pressure. So above a glass of water, there's a few water molecules that are just existing in the atmosphere right above that glass of water. If the liquid is in a closed container, then some of the vaporized molecules will return to the liquid. And that's what this animation is showing you, that the water molecules will come out, and then they'll go back in, and then they'll come out, and they'll go back in. When the number of molecules leaving and re-entering the liquid is equal, then they are in dynamic equilibrium. That's a term we're going to hear a lot later when we get into studying chemical equilibrium. And the pressure they create above the liquid is called the vapor pressure. So you're going to have at all times a certain number of molecules or moles of water above the water, and that's going to create a pressure, and that's called the vapor pressure. Since hot water has greater kinetic energy than cold water, hot water has greater vapor pressure. So that's what vapor pressure is. It's simply the pressure of whatever the substance is, the liquid substance is, that some of the molecules rise above it. They can go back down, they can come back out again, they can go back down, and that creates what's called vapor pressure right above the liquid. All right, now here's some more on vapor pressure. Substances with high vapor pressure evaporate faster than those with low vapor pressure. Substances that evaporate faster are said to be more volatile. So it's a different meaning of the word than what you often hear. Volatile, when it's used in everyday language, means something that explodes or catches on fire. But in chemistry, it has nothing to do with that. It simply means a substance that evaporates more easily than another. So the graph, this is called an energy distribution graph. So the graph shows the fraction of molecules at different kinetic energies. So this is the same number of molecules in both of these graphs here. It's just in one case it's at a higher temperature, and in the second case it's at the lower temperature. But the number of molecules, or the fraction of molecules, is the area under each of those curves. You can think of it as a percentage. So the percent of molecules is the area under those curves. So both of them have to be 100% of the molecules are underneath those curves. But what you see of the higher temperature one is it's got to be the same area under each of those curves because it's the same number of molecules. But the higher temperature one is a little bit lower on the left-hand side. But on the right-hand side, you can see that the pink line, the red line, is a little bit higher than the blue line. Now, what does that dashed line mean? That's the minimum kinetic energy that a molecule needs to escape from its liquid, to actually break from the liquid and become a gas molecule or a vapor molecule to get up above the liquid. So it has to be at that kinetic energy. Again, this is just a general graph here. It's not for any specific substance. So you can see at higher temperature, a greater fraction or a greater percentage of the molecules are to the right of that dashed line. That means that a greater percentage or a greater fraction of the molecules have enough energy to escape the liquid and go up above the liquid and become a vapor. So you should learn how to understand what this graph is saying. So let me continue to read. The dashed vertical line shows the minimum kinetic energy required to escape the liquid. The pink lower curve shows a greater fraction of the molecules to the right of the line and that have great enough kinetic energy to become vapor. Okay, so again, higher temperature is going to be a little bit lower curve, but it's going to be higher on the right-hand side of that dashed line. Boiling point. The boiling point of a liquid occurs when vapor pressure equals the atmospheric pressure pushing on the surface of the liquid. So when the liquid is pushing up, the molecules in the liquid are pushing up, which with as much pressure as the air, the atmosphere is pushing down on it, then the liquid starts to boil. The normal boiling point is the boiling point of a liquid at 1 atmosphere of pressure, basically what's inside the classroom. That's pretty much 1 atmosphere. At sea level, water at 1 atmosphere pressure boils at 100 degrees. In cooking, the water holds heat, which cooks the food. Above sea level, the pressure is less than 1 atmosphere, and the water boils at a lower temperature because there's less air pressure pushing down on the water, and therefore it's easier for the molecules to escape. So it boils at a lower temperature. But what that means is it means the food takes longer to cook because it can't get as hot. The water takes off before it's gotten as hot as it would have gotten down at sea level. It evaporates, it vaporizes. Okay, heating curves. So heating curves show the temperature increase or decrease associated with heat added or subtracted for a substance. The curve below is for water at 1 atmosphere. So let's take a look at what that's saying. Let's start at the bottom. So we're going to do this problem. We're going to do this. It's about the only numeric problem here. So what is happening, if you look at the graph, it has temperature on the vertical axis and heat added on the horizontal axis. So as you add more heat, that is to say, go to the right on the horizontal axis, you'll go up. You'll add the temperature on the vertical axis. So it's starting at negative 30 degrees, as you can see. And so this is ice that's frozen well below the freezing point of water. So as you add heat, the temperature goes up from negative 30 to negative 20 to negative 10 and finally to 0. Once it gets to 0, that's where the phase changes between water and ice. What happens is that the temperature stays the same as the ice starts to melt. The ice, you keep adding heat, so the ice is melting. But a funny thing happens. It doesn't get any warmer in terms of temperature. It stays at 0 degrees as long as the ice is melting. And as long as the ice is melting, it's 0 degrees. And then once all of the ice has melted, then you get to the point in the middle where the temperature starts going up again. You just have liquid water. And so the temperature goes from 0 degrees to 10, 20, 30, all the way up to 100 degrees. And you keep adding heat, the temperature will go up, as long as it's just water and not ice and not steam or anything else. Now, once it gets to 100 degrees, that's the boiling point of water. That's where water turns from liquid into vapor. The same thing happens as happened down below. That is, the temperature stays at 100 degrees. As long as the water is boiling, the liquid water cannot go above 100 degrees, because any molecule that has more energy than 100 degrees worth is going to fly away. It's going to become steam. So the water stays at 100 degrees. Then once all the water has evaporated and now you just have steam, you can increase the steam to a higher temperature than 100 degrees. And in this case, it's going up to, about 140 degrees, it looks like. So you have 5 different regions that you have to account for when you're going from ice to steam to vapor. And 3 of them are just ice, water, and steam, and 2 of them are the phase changes, going from ice to liquid water, and then going from liquid water to steam. So now we're going to work a problem here. Okay, so we're gonna solve this problem, and we have a problem that first of all, let's just look at the formulas we need. For the 3 regions where you have either ice or liquid water or steam, it's not changing, you use the equation that we used back when we were doing thermodynamics, which is Q equals mass times specific heat times change in temperature. So to compute the heat required to increase the temperature of a single state of matter, we use the specific heat equation. Each phase has its own specific heat, so you'll find the specific heat of ice is different than the specific heat of water. Now, for the phase change areas where the lines are flat, you use a different equation. To compute the heat energy required for the phase change, that is going from ice to liquid water or from liquid water to steam, we use the heat of vaporization equation. This is for liquid water to steam, to vapor. And that is heat equals the number of moles times the heat of vapor, the enthalpy of vaporization, delta H vaporization. The delta H vaporization for water is a known number. It's 40.67 kilojoules per mole. We're getting back into some of the terminology we used when we did thermodynamics. Now, for the heat of fusion, that's the heat required to melt ice, or it's the heat that has to come out if you want to freeze water into ice. So to compute the heat energy, I'm down at the bottom now, to compute the heat energy required for the phase change from solid ice to liquid water, we use the heat of fusion equation, which is Q, heat equals number of moles times heat of fusion. And the heat of fusion for water is 6.07 kilojoules per mole. Now you got to be careful when you do these problems, because you'll notice that the specific heat equation, the one over on the left, Q equals mc delta T, it requires that you use mass. That's what the M is for, mass. So you're using grams. But the two heat of vaporization and heat of fusion equations, notice they don't require mass, they require number of moles. So you have to be careful. If you're given mass in the question that you're being asked, you have to at some point convert to moles, and if you're given moles, you have to at some point convert to mass, because the equations use, one of them uses mass and the other two use number of moles. So let's work a problem. It's really not as hard as it seems. It's just plugging numbers into the equations and doing it in 5 different times. So here we go. So compute the heat in kilojoules to heat 1 mole of ice at negative 25 degrees centigrade to 125 degrees centigrade. Okay, so for this one, we're going to use the specific heat equation, Q equals mc delta T. So first, we have to take the moles. We were given moles, not mass, in grams. So we have to do, it's been a long time since we've done this, a molar mass conversion. 1 mole, and this is water, so it's 18.02 grams per mole, is going to give you how many grams of water. Now, the specific heat we're using is the specific heat of ice, not of liquid water. It's a different number. So it's 2.03 joules per gram Kelvin. And then finally, the temperature change is 25 K. Now, if you're observant, you may have noticed something. The temperatures were given to us in centigrade, not in Kelvin. So why can we say when it goes from negative 25 centigrade up to 0 degrees, because that's what region A is doing. It's increasing the temperature from negative 25 to 0. Why can we just say negative 25 degrees centigrade up to 0 degrees centigrade is the same in Kelvin? Because a degree in Kelvin is same as a degree in centigrade. If you increase the temperature by 25 degrees centigrade, that's also an increase of 25 degrees Kelvin. A degree on one scale is equal to a degree on the other. The only difference between the two scales is what they define as being 0. But as long as you're just dealing with temperature change, then you can go ahead and just say 25 Kelvin. It's going from some number of Kelvin. We don't even know what that number is. We just know it's going up by 25 degrees. So if you do the math on that, you end up with 0.91 kilojoules. And we're going to put that number up in the upper right-hand corner there, you see. Now we're going to go to section B. Now that's a phase change. That's going from ice to liquid water. The temperature stays the same during that, so you'll notice the temperature is not a part of the equation. It's simply Q equals moles times the enthalpy of fusion. Okay, so moles is 1. We were given that. We don't have to make a conversion. And the enthalpy of fusion for water is 6.01 kilojoules per mole. So you do the math on that and you end up with 6.01 kilojoules. And you can see we added that up in the upper right-hand corner. Now we're going to region C. We have to go back to the specific heat equation because it's an increase in temperature. So again, it's Q equals MC delta T. So, and we're going up 100 degrees from 0 degrees centigrade to 100 degrees centigrade. That's a 100-degree increase, which is the same on the centigrade scale, on the Kelvin scale rather, of going from 273 to 373. In other words, on both scales, it's 100 degrees. So don't let that point confuse you. If it's a temperature change, it doesn't matter which scale you use because 1 degree on Kelvin is the same as 1 degree centigrade. So all we're interested in is the temperature change, and it's a temperature change of 100 degrees. From 0 to 100 on the centigrade scale, and from 273 to 373 on the Kelvin scale. So here we go again. We've got to convert to grams because it asks for mass, so it's 1 mole times 18.02 grams per mole for water. And then now we have a number we've seen before many times. That's the specific heat of water, 4.18 joules per gram Kelvin. Back when we did thermal, we saw that number all the time. And the temperature change is 100 Kelvin. So you do the math and you get 7.52 kilojoules. So we put that up in the upper right-hand part of the slide. We're going to add that in. Now we're going on to region D. And again, it's a phase change. So this is the heat of vaporization equation. So Q equals moles times change in enthalpy of vaporization. So it's 1 mole, and that number is a well-known number. In chemistry, it's 40.067 kilojoules per mole. So that means the heat required to boil the water, that's what it's saying. How much heat is required to boil the water from all water to all steam is 40.67 kilojoules. And we add that in the upper right-hand part of the slide. And finally, on to the last part, we're going to take the steam, which is at 100 degrees as soon as it's boiled, and we're going to raise it up 25 degrees to 125 degrees. So again, that's a temperature change of 25 degrees on either scale. We have to use the Q equals MC delta T equation again, the same as we did before, and we end up with 8.30 kilojoules. So when we add all those 5 numbers together, the heat required, the enthalpy required to take ice at negative 25 degrees centigrade and turn it into steam at 125 degrees centigrade is 56 kilojoules. That's the number over on the right-hand side there. Now we're going to talk a little bit about solids before we wrap up this unit. So crystalline solids form organized structures with flat surfaces, often with flat surfaces. Examples would be diamonds or quartz. So you can see there's a crystalline solid. It's very organized. It's very much like a crystal lattice structure of an ionic compound. Amorphous solids have irregular arrangements of atoms. And good examples of that, which you're familiar with, are glass and rubber. And yeah, glass, even though glass seems very hard and very solid, its molecules are not put together necessarily. Sometimes they are, but not necessarily in a very orderly fashion. And so that's what an amorphous solid is. Okay, there's all kinds of geometry. If you like geometry, solids are kind of interesting because there's all kinds of geometry that goes along with solids. So crystalline solids can take on 14 different types of structure called Bravais lattices. Now you only need to know the first 3 of these. You don't have to memorize all of these, but you can see it's just to show you how many different arrangements of atoms and molecules can take place in a solid. So the first one we're going to talk about is called a simple, sometimes called primitive cubic model. Then 2 is the face-centered cubic, and 3 is the body-centered cubic arrangement. So let's take a look at them side by side. So simple cubic lattice structures have atoms at the corners of a cube. So there you see a cube, and it's not really the entire atom or molecule, it's just a piece of it. you can see that they've cut it off. Why have they cut it off like that? Because that forms a unit cell. What is a unit cell? We've talked about these before. If you took that structure, that unit cell, and you stacked them on top of each other and side by side to each other and front and back of each other and below each other and in every direction, and you just put those blocks side by side, just like little children's building blocks, just stacking them in all directions, you would end up with your lattice structure. So it's the smallest piece of that lattice structure that if you replicated it, repeated it, it would form that lattice structure. You can't just cut a lattice structure into any kind of block and repeat it and have it form the lattice. It won't work. So that is an example of the simplest kind, which is called a simple cubic lattice. Now, it has a coordination number of 6. Let's go down to the bottom and read what coordination number is. It's the number of atoms surrounding any atom in a lattice structure. So let me jump over to the model on the right, the body-centered cubic. It gives the best example of what a coordination number means, because it's the only one of the three where you see an entire whole spherical atom shown. So if you look at that spherical atom in the middle, that's what body-centered cubic means. How many different atoms do you see touching it? It's not entire atoms, but it's pieces of atoms. You see 1, 2, 3, 4 on the top, and down on the bottom you see 1, 2, 3, and then there's one on the other side that you can't see, so that's 4. So for a body-centered cubic, there's 8 different atoms of the identical type touching that central atom there. And so that's the coordination number. It's how many atoms are touching any particular atom. And that same number would be true of any atom in the lattice structure. All right, now let's go back to simple cubic, and we see it says that it has a coordination number of 6. Again, it's a little hard to tell because you don't see one entire atom in there, but if you were to round out one of those parts of an atom there, you would see that it has 6 different atoms touching it, actually touching it, not just near it, but actually touching it. And also another thing that they talk about with unit cells is the percent of the cube that's occupied by an atom. So for a simple cubic, 52% of the cube is occupied by one of those blue pieces of an atom. The other 48% is just empty space. And so down at the bottom, it explains that percent occupied, the percent of the unit cell that is occupied by atoms, the rest is empty space. Let's go to the middle, face-centered cubic. Well, that's one where you can see the atom is kind of on the face of the cube and it's cut in half. And so face-centered cubic unit cells have half an atom on each face and 1/8 an atom on the corners. This one you can kind of visualize if you have good spatial abilities. And that has a coordination number, it's pretty high, it's 12. So those 4, if you look at the one on the front face there, it has 4 partial atoms around its edges. And then it has some atoms, half atoms behind it, on top of it, to the left side of it, and down on the bottom. That gives you 8 in all. And then out towards you where you can't see any, it has 4 more. So that's a coordination number of 12 for a face-centered cubic. And 74% of the cube in a face-centered cubic is occupied by that turquoise color. The other 26% is empty space. And finally, we go back to the body-centered cubic. Those unit cells have a whole atom in the center and 1/8 of atoms on the corners. So you can see from that, as we did earlier, that the coordination number is 8 for that. And about 68% of that cube is occupied with those atoms or partial atoms, and the other 32% is just empty space. Okay, now we're going to get into molecular solids. So molecular solids are substances held together by intermolecular forces, either dispersion forces, dipole-dipole, or hydrogen bonds in a solid form. So generally, up until this point, we've been talking about the intermolecular forces bonding generally atoms that are in the form of gases or liquids. Now we're talking about intermolecular force that actually creates solids, where the molecules stay in place. So ice, frozen water, is the most common example of a molecular solid. Argon and carbon dioxide can also form solids at very low temperatures. Covalent network solids are formed by a large series of covalent bonds, similar to lattice structures. Diamonds are pure carbon atoms bonded in a 3-dimensional tetrahedral structure. So if you look closely at that diamond, you can see that they are formed, the black are the carbons, and the reds are the hydrogens, and you can see that they are forming tetrahedrons, and there are a bunch of tetrahedrons attached to each other in 3 dimensions. And that's what makes diamond such a hard element, is that it is a 3-dimensional network lattice. Now, graphite is interesting. That's over on the right-hand side. Graphite is a trigonal planar, and again, look at each of the levels of the graphite. Don't look at the whole structure, but look at just the top level. You can see that any one of those black dots is forming a trigonal planar arrangement with the other carbons. And so graphite is a trigonal planar arrangement of carbon atoms in layers that can slide across each other. Graphite is soft, and that's actually what's in your pencil. So in other words, those bonds between those trigonal planar bonds are pretty strong. They're carbon-carbon covalent bonds. But in between those layers, those are only held together, those layers, by weak intermolecular forces. And that is why that's why graphite is used in pencils. Because if you run your pencil across a piece of paper, it leaves one of those layers of graphite on the paper. And that's what's happening when you write with a pencil. So the bonds between the carbons on each level are strong, but the bonds between the different levels, the first, second, and third level you see there, are weak intermolecular forces. And that's the end of this video for Unit 8. It was fairly long, but it actually covers several days worth of material. So what I'm going to be doing is giving you some assignments. You can see there's not